Welcome to the Biophysics Sonification Group. We're a team of musicians and physicists who like to put sound to proteins. So let me tell you a little bit about protein folding. My name is Martin Grubel, and that's what I study. Proteins are chains of amino acids that usually start out disordered. So each amino acid here is one of those circles. But they can actually fold up into very regular structures. And I'll try to draw one down here at the bottom that's actually similar to what you're going to hear about in the rest of the vignette. And when proteins fold, they make a transition from disordered state to ordered states. And a kind of diagram that we like to draw in biophysics to indicate this is this funnel that has this order as its x-axis and the energy going down. I'll just write that as an E here, the energy going down along the y-axis. And so when a protein folds, it goes down this funnel and finally folds up into a well-defined structure. So they say that a picture is worth 1,000 words, and this is an example of a visualization, but a sound can also be worth 1,000 words. And so my musician colleague, Professor Steve Taylor, is going to tell you a little bit about what the music means that you've been hearing in the background while I was talking.
Hi, this is Steve Taylor. Here is a depiction of a protein known as the WW domain. Each amino acid is shown by a letter. I have also given each amino acid its own sound, from low for hydrophobic residues up to high for hydrophilic residues. Secondary structure, alpha helices and beta sheets, are given different percussive sounds. Altogether, this is an example of data-driven music. Everything you hear comes directly from the chain of amino acids that Martin was just drawing. Next, my colleagues Taras and Meredith will show us more about how these chains of amino acids fold into proteins.
Hello, my name is Meredith Rickard, and I'm a graduate student in Martin Grubela and Taras Pogorelov's labs. My research uses computational models to simulate protein folding in cellular environments. The cell is a very complex and crowded space. In fact, it's about as crowded as Times Square on New Year's Eve, pre-pandemic, of course. We're interested in learning how this crowded environment affects protein folding, so we've created an atom-by-atom model of a piece of the cell to see how the WW domain behaves inside of it. These models are useful to learn about the impact of the local environment on WW domain, but simpler models, like this simulation in water, are also crucial. One thing that is true across all of our models is that they are very complex, and sonification is a useful tool that allows us to hear hidden patterns in our data. To tell you more about how we sonify our data, I'm going to pass this off to Carla.
My name is Carla Scaletti, and I work on data sonification. In an all-atom fully solvated molecular dynamics simulation, there are hundreds of thousands of variables and millions of time steps. So one of the things we've been investigating is how we might use sound to help us interpret these massive data sets. In this example, we're using a rarity function to slow down time to help us identify straightforward versus unusual pathways between folded and unfolded states. Once the sound tells us where the potentially interesting time spans are, we can go back to the data and take a much closer look at those time intervals to determine what might be causing those unusual transitions. In this example, you can monitor one variable, the radius of gyration, with your ears, while at the same time you can use your eyes to monitor a 3D model of the way the protein shape changes over time. Even a highly simplified 2D lattice model of the WW domain can provide insights into the dynamics of the classic protein folding funnel. In this example, there are 740 possible shapes, displayed as stick figures on the right. The corresponding energy level of each shape is shown in the larger image on the left, with the highest energies at the top and the lowest energy fully folded state at the very bottom. Each state is also associated with a tone. The higher the frequency of the tone, the higher the energy of that state. So you can listen to different pathways between unfolded and folded states. In this example, you hear how a protein can get stuck in a misfolded intermediate state, or trap. In this example, you can hear when hydrogen bonds form in the simple lattice model. Native bonds are heard as synthesized plucked strings in the right channel, non-native bonds are heard as violin plucks an octave higher in the left channel, and shapes with no bonds are heard as filtered noise bursts. Data sonification is a powerful adjunct to data visualization, and using data sonification, we've recently discovered two very different folding pathways of the WW domain that weren't obvious from more conventional visualizations. We're working on a couple of papers to share these results with the research and education communities.